today, we're going to be talking about sort of neural networks 101. How do they work? At a high level, we're not going to really like dive into implementation or anything like that. We're going to get sort of into the weeds a little bit. And then sort of some of the large developments that have happened in the last 10 years in the machine learning world that are really just kind of sketching the outlines and how those things work and why transformers, the current hot thing, are so good. Uh, cool. Let's jump right into it. Oops. There we go. So, you know, Rudy actually covered a lot of this already. I used to work at Yeti. I currently work at a company called SourceGraph, which does AI code development tools. Cody is a plugin that you can get that can actually use the context of what you're working on to suggest completions to your code. It might sound very similar to another popular code product. And let's see, I'm really into functional programming. I am not an AI researcher. I studied this in college. I've studied this for fun. But feel free. I would say this is a very open presentation. Jump in with questions whenever you want. And you're very likely to stump me. You're very likely to ask something that I don't know, and I'll tell you, and I'll have suggestions for where to find the answer. But I do definitely want to say, definitely jump in wherever. There's going to be a lot of information, and it's probably going to be pretty fast. And if you have any questions, definitely speak up. Somebody else has that same question, and everything kind of builds on itself from this talk. So do not feel shy. Cool. Let's get started. So what we'll know by the end of this talk is really like a conversational understanding of how neural networks work. Like you'll be able to talk about them and sort of their inner workings, but not implement them. We'll have an idea of embeddings and what those are, and then some idea of how LLMs use those two techniques to get the results that they do. Stuff you're not going to know, unless you already know how to do it, is like how to program a neural network, exactly how a transformer works, all of the many different optimization architectures that exist. These are things like convolutional neural networks, or any of those things that really are just to make neural networks much better at handling a specific problem. We're just going to blast right past those. Cool. So the first thing to sort of cover, and this is more of just to demystify it, I think, is that you hear a lot when talking about machine learning, linear algebra, and specifically like high dimensional vectors. They'll talk about like, oh, well, we took these words, or we took this text and we embedded it in a 300 dimensional space. And that sounds very mystical. I remember when I was first studying math and hearing things like that, like how mathematicians work in these very high dimensional spaces, it sounds very, very mystical, but it's really not. So linear algebra, to go back, is the study of the matrix, and it feels very mystical, but it's really just matrix math. And matrix math is really just a way to do a lot of calculations faster. For the purposes of what machine learning does with them, it's not really doing anything that you couldn't do using traditional, multiplication and addition. It just does it much, much faster in a way that, say, like GPUs are already designed to do very, very quickly. So it's really just an optimization technique, but it does give rise. I mean, in linear algebra, you are very frequently talking about very high dimensional spaces and working with them, and that sounds very mystical. And I think the problem is that we often think about dimensionality really only like spatial dimensionality. We can understand two-dimensional spaces and three-dimensional spaces because we have a physical understanding of them. So then 4 or 5 or 300 dimensional spaces don't make a lot of sense. But an important sort of reframing is that really, when we talk about dimensionality in linear algebra, it's really much more of just like an Excel spreadsheet. So this spreadsheet, if we actually just look at, say, like the numbers, uh, the columns of the spreadsheet tell you the dimensionality. So this is a four-dimensional matrix, or a four-dimensional space that we're working with. And each entry is just a row in that matrix. And in very much the same way in machine learning, it is really just kind of spreadsheet data, where the columns are just going to represent the things we care about, which are potentially unrelated things like sales in each quarter. And each row is really going to be just like a distinct example data, a training data pointer or whatever. So when you hear somebody talking about this is embedded in a 300 dimensional space, really just think of that like, oh, this is an Excel spreadsheet that has 300 columns. It has 300 different variables that we're tracking. Cool. So now we can jump right into neural networks. So what is a neural network? Fundamentally, they are just a technique for approximating any mathematical function. So by that, I mean like f of x equals y, where x and y are just lists of numbers. And any function that can be represented as give me a list of numbers as an input, and I'll give you a list of numbers as an output, can be represented using a neural network and can be approximated using a neural network. There's only really, I say, three things that you need to create a neural network and train a neural network. And that is one, is exactly what we just talked about, a problem that can be represented numerically. This initially sounds like a little constraining, but we'll see very quickly that a lot of things can be sort of creatively rephrased as numerical problems. I sort of shy away from saying mathematical because they're not really going to be mathematical in the way that you traditionally think of. They're really just numerical. And then very importantly, we're going to need a way to grade the output of the network. So this is called a loss function. And this is really just a way of, I use the word grade specifically because it is really just saying like, did you get the right answer or did you get the wrong answer? When I gave you an example where I knew what the answer was, and how far from the right answer were you? And this, you can sort of get an insight. This is why things have to be represented numerically, because we need these quantitative values. We need to be able to say, you are exactly, 50 units away from the answer that I wanted. And finally, we just need a lot of examples of inputs with the output that we would expect for that. And this is how we are going to actually grade the function. We need to know what we're expecting to grade the network. So here is really a rough sketch of what a neural network looks like. It's not very pretty, but I'm only going to call out sort of a few things here. So the first is the input layer, and you can see here it has 3 nodes. So for this network, that is indicating that there is 3, the input would be basically a list with 3 numbers. So each one of those numbers corresponds to one of these nodes. And the output layer, you can see, just has a single node. So this network outputs just a single number as an output, or a list of a single number if you want to be consistent. And then there's a bunch of these layers in the middle, which are kind of arbitrary. They're really just there to, this sounds kind of funny, but they're really just there to make the network more complicated. The more complicated the network is, the more complicated questions it can answer. But we don't have to worry about how they're configured because they configure themselves. We don't have to, we literally just give the network a bunch of space to work. And then finally, the last thing is these arrows between the nodes. These are the connections between a node and the next node, or the next layer. Every node is connected to every node in the next layer. So you can see there's an arrow coming out of the input to every single one of these nodes in the next layer. And those edges, those connections, all they are just a single weight. Just every single one of these lines, you can think of as just, it's a single number. And so to calculate what goes into this top blue node, we could say, well, we're going to take the number that was in the first input, and then we're going to multiply it by the weight that is on this edge that corresponds here. We're going to do the same thing with the second input, multiply it by this weight, and we're going to do the same thing with the third input and multiply it by this weight. And then we're going to take all three of those numbers and add them together. And that's the input to this node. And then we'll do the same thing for every other network. So you can see that there's a lot of connections here. So this is the architecture of it. You'll probably have a lot of questions about like how do we instantiate all of these weights? How do we decide what these weights are? Initially, they're just random. Just pick any value you want. And then how do we actually like determine what the output means? And that's actually a good question, and I'll come back to that in a second. So I guess before I go into an example, anybody have any questions so far on this diagram and just the rough sketch of what is a neural network? Cool. All right. So here's something I'm going to link in the docs. There is this outstanding YouTuber called, named Grant Sanderson, but he runs a blog called 3 Blue 1 Brown. I can't recommend it enough. Amazing representations of mathematical concepts. He does fantastic deep dives into how to explain things. He did a 4-part series on neural networks that is far more in depth. I highly recommend it. It's linked in the docs, but we're just going to sort of use some of his examples. And so here's an example. This is a very traditional example of a use case for neural networks. And here he's actually built a really cool little widget. So this is a small little box here. I'll just clear this and I can draw a digit. So I'm going to draw, say, a 4. And this is just a matrix of, well, actually, you know what? Let's just see what it does first. I'll say check digit. It's going to push this through a neural network that it's already trained, and it's identified that I drew a 4. We could do this several times, and it's very accurate. So just take a second to step back and just imagine trying to write code that would do this, that would take in a picture of a black and white thing that a person has drawn and determine what digit it is. So how is this doing this? So if we jump down here, yeah, here's sort of a nice visualization of what's happening. You can see it is the thing that we drew on is a image, which is really just a matrix of pixels. Each pixel is a value from 0 to 1. 0 is black, 1 is white, anything in between is gray. So if this is a 28 by 28 pixel, we could think of that as just a list, sorry, 28 by 28 image. It's kind of just a list of 784 numbers that range from 0 to 1. So that could be an input to a neural network. All we'd have to do is really just take the matrix, break it apart, line them all up, and just treat them as our inputs. We have a whole bunch of layers in between, and then our output. Let's go back up to, or yeah, here we go. Our output. I'll go back to this guy. Is 10 nodes, where we are expecting a 1 in any one of those nodes indicates that that's the digit we think is written in the input. So this is kind of what I mean by this isn't really a traditionally mathematical problem, it's really just numerical. We have represented the photo as a list of numbers, and then we have an output, which is a list of 10 numbers where we are expecting to see a high value in only one position. And it works. It's kind of incredible. Any questions on that? That's kind of crazy.
So
I
do you?
have
Yeah.
sorry. So if you say that the nodes, the weights or the edges between the nodes,
Yes.
they adjust themselves as you like train this program.
Mm-hmm. Which we haven't
What
really gotten
exactly?
into.
Yeah. So maybe you'll touch on it later, but what does it mean for the weight to adjust itself? Is it just like a evolution of permutations of just randomly changing things, or does it intelligently like change its weights?
That's a very good question, and we are going to talk about it right coming up, so I am going to delay answering that.
Wait.
Anything else before somebody else, I think, had a question?
I had a similar question, I think. I mean, my understanding of it is that it's essentially like a lot of different, all the different layers are like probabilities that then output something. So is that like, I mean, when you say weights, it's basically like probability, right?
Not necessarily. So that's actually a really interesting perspective, because it actually highlights something very interesting, which is that we don't even necessarily know what the network is doing internally most of the time. You could definitely think of them as probabilities in a lot of cases, but the network is free to adjust its own weights however it decides. And so we can actually often get things where the internals of the network are doing something very surprising, that no human system would choose to do, but in the end, it does get the results that it needs. And this might also become a little more clear when we dive into how this works. Cool. Anything else? Cool. So yeah, let's jump into training. This is exactly right. When we've created this network, it has just completely random values. How do we get it to actually start to converge to being able to detect handwritten digits? So the first thing that we need is a large set of labeled data. This we talked about in the last thing. This is often going to be created just by a human, but it is an answer key. We just need lots and lots of examples of, here are example inputs and exactly what we think the output should be. This is kind of surprising, but this is really the secret sauce of a neural network. Like, there's a lot of other complicated, fancy things going on, but the labeled data is really what allows it to solve these really complicated problems. And so that is, even though it's such a simple thing, it's really worth calling out that, like, without these collections of data, or some way to produce labeled data, which maybe we'll talk about at the end, cases where you don't have it, you really are not going to get the incredible behavior that neural networks have. So we're going to start with that. And then we need a cost function. This is the other really important bit. So a cost function is that thing that we talked about. How do I grade the output of my network? And in this example, it's actually very simple. In most examples, it's actually pretty simple, but it is really where we get all of the semantics of what the network does. It's what actually, the cost function is the single thing that is going to determine what the network does, how it does it, and what the output of the network means. So let's look for an example at what is the cost function for this network. Intuitively, it's pretty simple, right? We're going to get 10 numbers as output, and we want one of those numbers to be a 1, and we want everything else to be a 0. So the simplest way we could calculate the cost is to just say, well, let's just look at what the network output for each number, and let's take the difference from what we think the answer should have been. And then let's add all of those together. And the total will now be the cost. And that's a good first approximation, except we don't have any constraints on the output. So we might actually have negative values, or in turn, we might have negative values coming out of the calculation. And if we had a whole bunch of positive values and negative values and we sum them all together, we're actually going to get a lower cost than we would have expected. And that's not broken, but it's not sort of a good representation of how bad that answer was. So a very simple sort of like hack to fix that is to just let's square everything. And then we're sort of guaranteed that the values will all be positive. And so now we can add them all together. And we know that the farther the distance from any expected answer is, we will always have a larger and larger positive cost. And as we get closer and closer to actually having exactly the vector that we want, all zeros and then a 1 in the 3, the cost will get smaller and smaller. This is just one cost function. I could come up with any other function that I wanted, so long as it had the property that a vector that looks like this one on the left produces a much larger value than the vector on the right. And so this is a pretty arbitrary choice, and this is just a convenient one for our specific use case. So the cost function is really how we tell the network what we expect it to do. And it's also, you might notice that like this labeling of the top output is 0 and the bottom output is 9 is totally arbitrary. We could actually flip the whole network. We could go top to bottom. We could scatter the labels. Just so long as we made the cost function align to what our semantics are, we can make the network, output, the prediction in whatever spot we want. So this is really how the cost function dictates what the network should do. Not necessarily that it does that, but what it should do. Cool. All right. Now the final step is exactly what you were both asking about. And I'm actually going to kind of do a pretty cursory go over it, but we can talk more about sort of the lower details. So the last step is what's called backpropagation. This is how we actually determine how to update every single weight in the matrix, or sorry, in the network. And I'm not going to go into the weeds of it because it is a pretty sort of mechanical derivation. And it's also not where the magic happens. Like as we talked about before, the magic happens from the labeled data and from the cost function. Those are the decisions that somebody has to make to determine what the network will do. Backpropagation is just a step to make that happen. But to give you a little more detail, because you were curious, what we're going to do is we can use the cost function and the network itself. Now, you can think of the entire network as just a huge mathematical expression, right? Because every node is just comprised of the sum of the products of the weights from the previous layer and the values in the previous layer. So it's just a big, huge collection of pluses and multiplies. And we have a cost function which tells us how wrong the answer was. We can use the cost function to calculate exactly how much every single weight in the network contributed to the error in the cost by doing a partial derivative. So we can now say for every single weight, oh, this actually contributed to the right answer. This would have contributed to the right answer. This would have contributed to the wrong answer. And we can use that to update every single weight in the network a little bit, just a small nudge in the direction of minimizing the cost. And we don't want to make huge steps because they will sort of interact with each other and we can get bad behavior. But we'll make a small iteration, small change, and then just lather, rinse, repeat over and over and over and over again until our network is outputting something that is very close to our expected behavior. This handwritten digits thing has like a 99.7% accuracy. Does that give you more clarity on sort of how the numbers are updated, or would you like any more detail?
Yeah, I think that makes sense.
Oh, go ahead, Johnny.
Oh, I have an unrelated question. So if yours is more directly related, go ahead.
So yeah, I guess like are the people that are running, whoever's running the model, are you able to modify weights in the intermediate layers, or is that all automated?
Yes.
Okay.
Yeah, yes. Every part of this is automated. So you can actually do this on paper, but you can. So the very first step is you would say, okay, given the output of the network and the cost associated with this single example, what was the difference? Or sorry, how much did the output contribute to the error in the how much did the input influence the cost? It's going to be very, very linear, right? Because there's no steps in between. So it's going to be very, very high. But we can't adjust the output at all, right? The output is simply the connections from, the result of all of these cascading calculations. So we can take it one step back and we can say, let's look at, let's get an actual network going. Where was it? Here. So yeah, whoops. So you take it one step back and say, okay, how much did this weight contribute to the cost? And we can simply calculate how much does a change to this weight impact the output, and how much does the output impact the cost? And so that will tell us how much to adjust this weight. And then we can go even further back and say, how much did this weight contribute to the output of this node, which contributed to this weight, which contributed to this output, which contributed to this, and all the way back. And that's why it's called backwards propagation or backwards chaining, because like you are really working from this node and saying like, okay, this was wrong. How much did each of these contribute to that being wrong? And for each of them, how much did each of its incoming weights impact how it was wrong, et cetera, et cetera, et cetera. So you can take this all the way back to these initial weights coming out of the inputs, and you are just going to adjust every single one. Is that more clear?
Mm-hmm.
Cool.
I had a question about the cost function and the wrongness of a result. So you'd mentioned that like this particular like letter or number recognition AI gets it like 99.7% right. So I'm curious, like, how are we defining rightness or wrongness? Is it the labeled data? So like if you have 1,000 bits of labeled data and it gets it right 997 out of 1,000 or something along those lines, is that what that means?
Yes, exactly. And I mean, to be a little more pedantic, the way you would actually do this is you would have, say, 1,000 training examples, and you would have 100 testing examples. And we would do this exact process that we've been talking about on our 1,000 examples. But when we want to measure the accuracy of the network, we'll actually run it on those 100 testing examples where it has never seen those examples before. We do not update the network based on those testing examples. And so this sort of ensures that it's not just learning how to memorize all of the inputs that it's seen before and like it just knows what answer to give. We are going to test it on fresh data that we know the answer to and see how it does there on like actual new instances of this problem.
Gotcha. So then when we say that it's 99.7% accurate or whatever, does that mean like on the test data, it was 99.7? And so someone's going into the test data and retroactively grading it, essentially?
Yeah, exactly. Somebody is feeding it all of that test data and saying like, okay, how did it do? Yeah,
Gotcha.
exactly. Anything else? We're going to move on from neural networks after this. So if there is any more questions on sort of these broad
Yeah,
strokes.
James,
Yeah.
I'm not sure. So
Mhm.
conceptually, I understand like, what you're talking about for neural networks. Is
Mhm.
there like a specific, I imagine there's lots of them, but there's like
Mhm.
specific programs that run neural networks that you do
Mhm.
like plug in the inputs and outputs for? Like,
Mhm.
could you touch on like what the most popular ones are or like,
Yeah. Yeah, definitely. So I'll start by saying you don't need a library. Like something I did in college was literally to write neural networks completely from scratch. There is nothing more to them than what we've talked about here. However, you are completely right. You don't want to do this because one, the implementation that I wrote was so painfully slow that like trying to train it to do digits took forever. Um, and also there are, as we hit on with the linear algebra stuff, enormous amounts of optimizations that can be unlocked at a hardware level. So with that said, the most popular open source frameworks for a long time, TensorFlow was really well, actually, no, even before that, you would go back to like the NumPy days. There were things like scikit-learn, and there was another one that was part of NumPy. I'm forgetting. But anyway, those were sort of the early days. They used the underlying C libraries to get a lot of speed and a lot of matrix math. They're still very powerful, but Google released TensorFlow about 8 years ago, and that really became the de facto. Um, it's extremely powerful. It runs in a ton of different, you can sort of specify, I want to train this for running on mobile, I want to train this for running wherever. It has a huge number of configuration features. Um, and it's also implemented in many different languages. So you can talk to it from JavaScript, you can talk to it from Python, you can talk to it. Recently, it has been losing ground, losing market share to PyTorch, which is largely backed by Facebook. It's completely open source. It's not actually like part of any organization. So that's one of the things that people find attractive. It's also it's very good at integrating with different CPU or different hardware components. So it really wins well on that. And finally, something actually both of these libraries do, which is really cool, which is we talked about how you implement a cost function and then you would have to calculate how to um, calculate the derivative, the partial derivative for every single weight in your matrix in your neural network. And that is something that like going back to like scikit-learn and stuff like that, you just did by hand. You took your network and you wrote programs to do the derivative for everything. And it's a lot of work. It's a lot of math. It's very easy to get it wrong. You try to automate parts of it, but it's automating doing like calculus analysis. It's a hard thing to do. I made a lot of mistakes doing this. Um, Both TensorFlow and PyTorch actually have what they call a gradient framework in it, where you define a cost function and you define your network, and it will automatically derive the partial derivatives for every single node in your network. And then automatically you can just say dot backprop, and it will push all of it will adjust all of the weights in the network automatically. So that is a huge, not just quality of life, but these networks have gotten so complicated and some of the operations so complex that it's a real godsend. Cool. Anything
Um,
else?
I,
Yeah.
I have a question about the hidden layers.
Yeah.
Um, so I guess what I'm thinking is like it seems like the hidden layers are kind of maybe abstract or dynamic or sort of a
Mhm.
black box in a lot of
Mhm.
ways. But I guess what I'm thinking of in the example you gave is like, is at some level, is it possible to think of the different hidden layers as like, for example, like, is the pixel to the left of me black or white?
Mhm.
Something.
Such a fantastic question. And I cannot recommend enough reading either reading this or watching the YouTube video because this is exactly something that he talks about a lot in this video. Um, Yes, that seems like such a logical, where even is it? It seems like such a logical thing to think like, oh, that's probably what the network is doing. We call it feature detection. It's probably learning how to break up, is it in here? No, it's probably learning how to like break up the image into small components and like detect small parts of the image. Yeah, so here, for example, he's saying like maybe this layer is learning how to detect edges, and this layer is learning how to detect shapes that are drawn like this, and then the last layer is just putting those together to find patterns and say, oh, if it has this shape and this shape, then it's a digit. But with traditional neural networks, absolutely not. They are doing the most, they're just doing anything to make the pattern work. So here, this is sort of a visualization of the heat map of what every layer is looking for to determine the digit. It looks nothing, none of these look anything like a digit. Uh, and so there's very interesting edge cases to this where if you take an input that looks like this, like any one of these, it will very confidently tell you it's some digit. It'll be like, that's a 7. That's the most 7 I've ever seen. That is textbook 7. And this is actually a big failing of traditional neural networks is there is no limitation on how the hidden layers work. And so they will not actually align to our expectation of how you would solve this problem. They will discover their own way of solving the problem that might not extend to input types that it's never seen before, right? A big part of the problem is it never saw any inputs that were just static noise. So now, something I'm not going to talk about too much, but there is a separate approach to processing specifically images or spatial data that's called convolutional neural networks. And those by nature do actually do a lot. Their hidden layers are much more likely to do exactly the sort of feature detection that you are talking about. You can go in and look at some of the hidden layers in convolutional neural networks and see like, this is doing edge detection. It's doing it in a different way than we would expect, but it's definitely doing that. So there are networks that do that, but that is not necessarily traditional feed forward networks, which is what these are called, are just absolute chaos in the hidden layers.
Cool. That's super interesting.
Yeah, it's very surprising. It's crazy they get the results they do. Cool. Anything else? Awesome. All right. So next up, I want to talk about embeddings. This is something that we hear a lot. They're used a lot, and I just think they're so cool. So I wanted to take some time to talk about them. So embeddings started with a project called Word2Vec, which was a Google project by this guy, Jeff Dean, and Sanjay Gedawaan, who was his programming partner. Never heard of the two of them. I would say like look them up because they have built more things than you would imagine. They're like some of the most prolific engineers. Anyway, the fundamental problem that they were running into is how do we encode text as numbers? This doesn't seem like a hard problem, right? Like our first example was like, let's look at a picture and represent it as a huge stream of numbers. And we had no problems with that. And we encode text as numbers every single day, right? So why is this hard? And there's something that I kind of didn't talk about. It's not a requirement for neural networks, but it does help. And that is something called locality. So if you think about the image, the handwritten digits, if I introduce random noise, if I change 1 pixel or 5 pixels or 20 pixels, how likely is that to actually change what is the digit that is in that picture? It's very unlikely. You can make lots of random small, jitter to the image, and it's still the same image. It's still very recognizably the same image. And that is something that's what we call locality. Images have very high locality. But text and really language at large does not. For for example, think of words that you can change one letter and the meaning is completely different. Claimed and clammed are very different words, but both written phonetically or in a UTF-8 representation, they're extremely close to each other. And so this causes a lot of problems. If you are trying to train a network that takes its input as, say, UTF-8 and outputs UTF-8 or ASCII, well, subset anyway, you get a lot of, it's very, very, very slow to train. And a lot of those outputs are just not going to be words, right? They're just going to be, if you're just outputting 20 letters encoded in UTF-8, most of those are not going to be words. And it's going to be very, very hard to get the network to converge on, predicting the next word or predicting what word's misspelled, whatever problem you're trying to train it on. So the technique that most researchers were using to represent text is what's called a one-hot encoding. I pick 10,000 or 1,000 or 50,000 words, and then I'm going to represent every word as a list of that length. So let's say it's 10,000. Every word is represented by a 10,000 element list, where the nth element of that list is a 1 if it's the nth word in my vocabulary. So here, have a good day, have is 1, a is 2, good is 3. And you can see the position of each 1 is telling us like what word it is. We're basically just giving a flag to every single word in the vocabulary. So this has a benefit where at the output, if I'm outputting a word that is a one-hot vector, it's very similar to the classification problem we had in handwriting digits. Like, it's very easy to say, okay, just find the highest digit and say that is the word I'm looking for, or that the highest digit tells me it's the nth word, whatever. So you have a much better representation. It's much easier to sort of interpret inputs and outputs. But it's extremely huge. The inputs are huge. And if you think every single node in the input layer is connected to every single node in the next layer, there's a huge amount of connections. And then we're going to have this exact same problem on the output layer, where if I'm going out to 10,000 from, say, 300, I have 300 nodes in the last layer, and it's going out to 10,000. That is huge number of connections, and the more connections, the more time it's going to take to train, the more time it's going to take to converge, and time is money with neural networks. So first of all, does the idea of sort of what a one-hot encoding is make sense to people? It's just kind of a convention. Cool. Actually, one more benefit about one-hot encodings is that it is also easy to represent a collection of words. Right? I could represent have a good day in one vector by just having it be 1, 1, 1, 1, zeros. Right? That's a logical way to represent 4 words together. You don't have any idea about the order of those words, but it's still sort of convenient. So, with all that said, word2vec was a very interesting problem where they said, okay, we are going to take, I think it was 10,000 words in our input, and we are going to do next word prediction. So we're going to take, say, 10 words from we have a huge collection of, I think it was from Google Books. You just took you took a chunk of 10 words, you one-hot encode each of them, you add them all together so that you have this sort of this collection of 10 words, you feed it into the network, and it's going to output a vector of 10,000, hopefully with a 1 corresponding to the word that is next in the input. And this was a pretty traditional style of problem to solve with word encodings at the time. This was like 2015 or so. But they did something very different, which is that they made the internal layer, and it was only a single hidden layer, they made it much, much, much smaller than the input or output layers. So I think they had 10,000 nodes in the input and output, but there was only 300 nodes in the middle layer. So it was trying to represent words, of which to it was represented as 10,000 vectors, elements of 10,000 vector, but it did not have anywhere near enough space to represent those words as 10,000 element vectors. It had to, in effect, learn an extremely dense representation of words if it wanted to get better at this problem. So that's exactly what it did. So for example, if I have 10,000 here, I have 300 nodes in the input layer. We can actually say it's learning a 300 element representation of each word. And what was really, they ran this experiment. It took a long time, but it did get good behavior. But what was really exciting about it was that when they looked at the sort of 300 element representation of every single word that they trained it on, it had learned semantics. It hadn't learned sort of to just represent words, but it learned what words meant by looking at how words appeared next to each other in text. And those embeddings, which is what they would call those sort of 300 element vectors, they represented semantics, and you could do mathematics with them. So a very famous example from the paper was you would get sort of a representation for, say, like the word king and the word man and the word woman, and then you could do mathematics on those vectors, right? You could just say, okay, let's take the vector for the representation of king, and let's subtract out the representation of the word man, and let's add to it the representation of the word woman. And you got an output vector which was very close to the vector that represented the word queen. So the network, without being asked to, it was only really asked to represent, to predict the next word. But since it was so constrained, it learned how to sort of represent the semantics of, traditional gender in text. So this was a huge breakthrough in very efficient ways to represent text inside of a network. People found that if you translated words into embeddings of the word and then started your problem using the embedding, instead of just using like a one-hot encoding of the text, your network would converge to appropriate or good behavior way faster, because what the network is internally trying to do is basically do math with vectors, do math with all of these representations of words, and now that math makes sense. So huge breakthrough that kind of happened a little bit by accident. Questions on embeddings?
I mean, that's kind of crazy. So like
It's absolutely
there's
crazy.
there's some way in which like introducing that constraint in this middle layer like forced the process to condense into like a richer
Exactly.
space, kind of.
Exactly. And this was their theory going in, but I don't think a lot of people expected it to work. There's actually calculators for this. If you search for like embeddings calculator, there are websites where people have taken like the original data set, and you can exactly literally do these calculations and just see like what does yesterday plus what does 2 days ago plus yesterday equal, and you'll get a vector close to yesterday or something like that. Like it has learned many different dimensionalities of language and semantics. And it only happened because the network was so constrained. And this has actually led to people, selectively introducing very constrained, very tight hidden layers to try to mimic these embedding behavior. Anything else? All right, I'm very conscious of time, so we're going to kind of fly through the last section. So I'm probably just going to do this very quickly. So everything we've talked about so far is about a single instance of data, and then what is the answer for that, right? Here is an image, tell me what picture is in it. Here is a collection of words, tell me what word comes next. But a lot of the things we see today are sort of continuous, right? I want to look at a video and I want to answer a question. I want to look at I want to give you a couple of words and I want you to tell me all of the words that come after this. I want you to give me sort of a variable length output. There were a lot of approaches that didn't work. I'm going to just skip the whole rest of that. Transformers are the most recent, I got to be probably like the 50,000th person to have a thing about Transformers with a Transformers image. Now, Transformers are this. Transformers are a innovation also from Google 2016 about how do I handle huge collections of text, originally just text, now it's been extended to many different data types, where I need things to depend on, I want to look at many different problems at once. So for example, I'm doing word prediction, what comes next, but I'm looking at a huge window of text. And I want to specifically understand what we call long-range dependencies. I think I have an example in here, yeah. Human language has a lot of long-range dependencies. If I said, Sean went to the store and blank, he depends, like predicting the word he means I have to go all the way back to Sean, and then I have to have some concept about what Sean means and what word would follow from that. Most of the approaches that we previously had did not handle this well at all, because you would inevitably get a linear drop off as you were moving through the text to each word sort of depending less and less and less. Transformers introduced an idea called self-attention, and this is really what made Transformers so popular and what unlocked these crazy breakthroughs. And the idea here is I have a huge window of input, and I also have something that I am focusing on. For self-attention, it's literally, given this sentence, how much does every word in the sentence depend on each word in the sentence? And so I'm literally going to build a matrix that is, n by n. In the case of ChatGPT, it's like 4096 by 4096. That's how many words it's looking at a time. And I'm going to create a sort of cross matrix of how much does each word depend on every other word in the sentence? What informs the importance of each word? And unlike past approaches, this was a completely dynamic calculation. The network internally would learn this, how much each word should depend on each other word. And that was a variable in the network that would then be trained along with every other element, every other weight, and every other factor in the network. So those could change through time. It could dynamically learn when to pay more attention to one word or when to pay more attention to another. And that dynamic approach ended up being enormously successful. And it's really what unlocked very useful long-term or long-range text generation. Without self-attention or then cross-attention, which maybe we'll get to talk about, you wouldn't be able to get text out of ChatGPT that really sounds like a human. I don't think we'll have time to talk about this. So let's just stop right there. Are there any questions sort of about this, about Transformers, this idea? I guess anything, because we just have 2 minutes left, so.
I had one question about this. So you kind of talked about the last bit, the embeddings as like the semantics. So relating things semantically.
Yep.
Would it be fair to talk about this as relating things syntactically? So like recognizing how the syntactic structure of a sentence creates
Yes.
interdependence between words?
Yes, except I would say that I would even go further and say it is translating. This is how we translate the syntax. Embeddings was how we represented the syntax of words into the semantics of words. Self-attention is how we translate the syntax of sentences into the semantics of sentences.
Yeah.
Like literally, we are going to take the embeddings of each of these words, take the cross attention or the self-attention of the sentence, and then take all of those representations and just add them together. And that is now going to be our representation going forward of the word it. It's going to add the representation of the animal, and to a certain degree, the amount that we weight it by will come from this attention value.
And does this equally depend on like there being some sort of answer key to train on, like some way
Yes.
for us to introduce to the system, like, hey, this is what we're looking for with this attention?
Yes, exactly. So this is an important thing, is that like GPT, for example, is trained it has multiple training stages, but the vast majority of its training is done exactly like this problem. It is, oh, I don't have it written anywhere, but it is exactly just saying, here is 20 words from the internet, what comes next? And it is going to use all of this stuff internally, but at the end of the day, it really is just a neural network. It is just saying, okay, I have all of these calculations and I output saying that the next word should be blank. And we're going to say, no, actually, the next word in Wikipedia was this. So update all of your weights to get a little bit closer to saying this word next time.
James, I want to be respectful of your time. Do you need to?
I don't have anything after this, but I'm also
Okay.
anybody who needs to drop, please go ahead.
All right, I just wanted to make sure that we weren't keeping you. I think everyone can maybe stay for another 5 minutes from just at least looking at the calendar in case there's any other last questions. Johnny and Will might just keep going if we let him know. So I might need to especially Johnny. I can tell he's already got more ready to go, but we can ask James a couple more and then we can let him go.
Here, I'll just give a quick of like some of the stuff we didn't talk about. If there's any questions on this stuff too, we can also quickly go through any of them. We didn't talk about reinforcement learning. Reinforcement learning is basically, what if I don't have a labeled data set, but I know how to identify good things when I see them? This comes up a lot in game playing. We didn't talk about reinforcement learning with human feedback, which is how ChatGPT is trained in its final stages to actually give good responses. These are really cool. Generative AI, like it's a big buzzword. The key insight here is that really generative AI is just about how do I rephrase the problem that I'm trying to solve so that it is just a traditional neural network. All of these really come down to that. So all of these are, how do I just do one step so that this becomes a traditional neural network with labeled training data, and then keep going. Cool. Annie, open season.
Okay, I've got like 1,000 philosophical questions that I won't ask. I'll push those on the side. Concretely speaking, so you work at SourceGraph, which is Cody, or
Yeah.
they've created Cody, right? So
Mhm.
I use Cody, and it's really interesting. It's fantastic. What sort of like training did you guys do in order to get it to predict the right kinds of things coming next? Was it just like a huge repository of code data, or what did that look? I mean, obviously it's also outputting English, so it can't just be code data. So just what does that process look like for you guys?
We literally use OpenAI. So the next question is, what did OpenAI do? OpenAI, it's actually exactly this. It's all the same. Like OpenAI, so GitHub Copilot and Cody are both based on Codex, which is their transformer model that's just trained on code. But it's literally just trained on code. Like they just took the exact architecture that they used for GPT-3 and just limited its training data to only GitHub's public repositories, which is like 2 billion lines of code. And it's just doing next character prediction. They just did that over and over again. And it's just learning to predict the next character. Now, the only sort of missing piece here is, okay, but it doesn't just generate the next character, right? It generates dozens of characters, it generates sometimes thousands of characters. The only piece that's really missing here is in the language that GPT or really any of these architectures have, they have a special token that is called a stop token. And all you need to do to get these things to generate arbitrarily is recursively run them with, like, once it makes a generation of what comes next, add that to the window and then rerun it. And then do that again and do that again until it gives you the stop token, until it says, okay, I'm done predicting. And that's how you get large windows. I mean, there's a ton of optimizations and a ton of sort of minutia here, but at a fundamental idea, that's really all it's doing.
One or two more questions? Anyone besides Johnny before he probably said he could just take up the last question? Sounds like
Just a comment, but
Mhm.
James was up in our office in San Francisco doing matrix math 10 years ago when we were doing
I remember we
optics.
were up at like 3 a.m. doing it on a whiteboard.
Yeah, we don't do that anymore, but yeah.
Me neither. Not at 3 a.m. at least.
Johnny, you want to use the last one? You got one more locked and loaded?
Okay, this one I asked the other guy this, again, more practically oriented. How successful do you think these sorts of things will be at essentially being coders in the next 5 years?
Ugh, I vacillate like every day depending on what I've seen Cody do that day. I am generally enormously optimistic, which also is kind of one of the reasons that I actually left my previous company to join SourceGraph, is I was like, this is such a huge change. Um, and I think there's still so much more for it to go. And the road is pretty clear, right? It's not like, okay, we've hit this level of ability with these bots, but we have no idea how we're going to get them better. We do know how we're going to make them better. They're already working on that. So I don't see this slowing down anytime soon. The problems where it's still very bad are, so it is incredible at doing greenfield projects that have, say, limited dependencies. For example, this seems like this is crazy, but I actually did this a couple months ago. Try to write a programming language with a code assistant. They're incredible. They are so much better than I am at writing this code. But once you start to ask it about, like, once you start working on a very gnarly, client code base that has tens of thousands or hundreds of thousands or a million lines of code with lots of integrations with different libraries and things like that, it does start to break down because it's starting to see things that it really hasn't seen before. It doesn't have much insight. And that is a much harder problem. So I can see that as being a frontier for a long time, where it's a lot harder to like answer questions about a really specific code base, but it's extremely good at building new features, for example, which is kind of a shame because that's like the most fun thing to do. But yeah, that's how I feel about it today. Ask me again tomorrow.